The biggest toothed predator on Earth holds its breath and drops straight down into total darkness. A sperm whale, 52 feet long, nearly 45 tons, and it comes back scarred every time. We know what lives above the surface. We have maps, cameras, submarines. But below the whale, past 10,000 feet, the ocean turns into something we barely understand. We will go down there together, through the crushing dark, past creatures with no eyes, and mouths bigger than their bodies, all the way to a zone where the pressure alone should kill anything breathing air. If you enjoy the journey, like and subscribe. It helps more than you know. Now take a breath. We begin.
Picture the biggest animal you have ever seen in person. A school bus, maybe two. Now stack them end to end and give the whole thing teeth. That is a male sperm whale, 52 feet long, nearly 45 tons, the largest toothed predator alive on this planet right now. And it has scars. Round ones, dozens of them, pressed into the skin like someone pushed a coffee mug against the whale's body and twisted. Some circles are 6 inches across, some are bigger. They run along the head, the sides, even the jaw. Scientists who study these animals up close say the patterns are consistent across whales, from completely different oceans, same shape, same placement. For a long time, people assumed the scars came from fights with other whales, territorial battles, accidents, but the geometry was wrong. The marks were too round, too uniform, too spread in clusters that matched something specific, something with multiple contact points arranged in a ring. That is when researchers started looking at what sperm whales eat. Squid, specifically, very large squid, animals with arms lined with suckers, and in some species, those suckers have hard, sharp hooks around the edges. When a squid locks onto something and pulls, it leaves a mark shaped exactly like the ones covering these whales. So the scars are evidence, physical proof that something happened down there in the dark. A fight, a struggle, something that left a mark on an animal the size of a city bus. Here is what makes it stranger. Sperm whales win those fights almost every time. They are the hunters. They go down looking for prey, but they still come back carrying the damage. The prey fought back hard enough to scar the most powerful toothed animal in the ocean. That raises one question immediately. If a sperm whale comes back looking like that, what exactly is it running into down there? Scientists have spent decades trying to answer that. They have found squid beaks in whale stomachs. They have measured the scar patterns. They have tracked dive depths and recorded sounds coming from thousands of feet below the surface. And every answer they find opens 2 more questions. What we do know is this: sperm whales do not avoid the deep. They choose it. Every single day they fill their lungs at the surface, angle their massive bodies downward, and disappear. They stay down for 45 minutes on a routine dive. Sometimes longer, sometimes much deeper than anyone expected. They are going somewhere specific, hunting something specific. And whatever they find down there is strong enough, fast enough, or strange enough to leave marks on the toughest predator in the sea. The whale surfaces. It breathes. It rests. Then it goes back down. It does this over and over every day of its life. That is the first thing you need to understand. This animal is not accidentally stumbling into danger. It is returning to it on purpose. That tells you something important about what waits below. Because before we can understand what lives in that darkness, we need to understand the animal willing to enter it. And the more you learn about the sperm whale's body, the more you realize it was engineered for exactly this kind of mission. Something down there shaped this animal, and we are about to find out what. Everything about a sperm whale looks wrong until you understand what it was built for. The head is enormous. On a full-grown male, it takes up more than 1/3 of the entire body length. That is roughly 17 feet of skull on a 52-foot animal. If you stood next to it, the head alone would be taller than your house. From the side, it looks almost rectangular, like a submarine with a face. Most animals have heads proportional to their bodies. A sperm whale does not. And that disproportionate head is the first clue that this animal was designed around a specific problem. The problem is hunting in total darkness, 2,000 feet underwater. Inside that massive head sits one of the most sophisticated biological sonar systems ever studied. Scientists call the main structure the spermaceti organ. It is a cavity filled with a waxy oil, and the whale uses it to focus and fire clicks at extreme precision. Those clicks travel through the water, hit something ahead of the whale, and bounce back. The whale reads the echo. Instant picture. Shape, distance, movement, all of it built from sound in a place where eyes are useless. Think of it like a submarine's sonar, but alive, packed into an animal's forehead and running on 0 batteries. The lower jaw is narrow and mostly bone. The teeth sit only on the bottom row, and they fit into sockets in the upper jaw when the mouth closes. The inside of the mouth is often startlingly white, bright against the dark skin outside. When the whale opens it, you see a pale interior lined with cone-shaped teeth that can be 7 inches long each. Those teeth are for gripping. The whale does not chew. It grabs its prey in the dark and swallows it whole. The skin is different too. Behind the head, it runs in deep folds and wrinkles, almost like old leather that has been bunched up. Scientists believe those folds help the skin handle the pressure changes that come with extreme dives. The body is built to compress and expand without tearing. The circulatory system is another adaptation. Sperm whales carry an enormous volume of blood relative to their body size, and that blood holds an unusually high concentration of oxygen-binding proteins. Before a dive, the whale effectively preloads its muscles and blood with oxygen, the same way a diver hyperventilates, but far more efficient and built directly into the biology. The spleen is massive. In deep-diving marine mammals, the spleen acts as a reserve tank, storing red blood cells and releasing them into circulation at depth to extend the oxygen supply. A sperm whale's spleen is proportionally huge, and here is the part that still surprises people. On a deep dive, the whale's heart rate drops dramatically. Its blood flow reroutes away from non-essential muscles and toward the brain and heart. The animal essentially powers down everything it does not need and runs on minimum energy to buy more time at depth. Every single one of these features points to the same conclusion. Something in the deep ocean was worth this level of investment, worth evolving a body that could handle pressure, darkness, and oxygen starvation just to get there. The whale did not stumble into the abyss. Evolution sent it there. And what the whale finds when it arrives, the prey it hunts in that crushing dark, turns out to be stranger and more dangerous than almost anything living near the surface. The ocean has layers. Most people know the top one because that is where sunlight hits and fish swim near boats and dolphins leap out of the water. But beneath that bright, familiar layer, the ocean keeps going, and it gets stranger the deeper you travel. Scientists divide the ocean into zones based on how much light reaches them. The top layer goes from the surface down to about 650 feet. Sunlight floods through it. Photosynthesis happens here. Plants grow, small fish swarm. It looks like an underwater version of a sunny meadow. This is where most ocean life that people think of actually lives. Below that, from about 650 feet to 3,300 feet, the light fades to a dim blue-grey. Some animals here have enormous eyes built to catch the last traces of light. Others are transparent, nearly invisible in the murk. Predators lurk here that most people have never heard of, and the hunting gets harder with every foot you descend. Deeper still, from 3,300 feet down to about 13,000 feet, there is no light at all. Zero. Complete darkness. The pressure at this level would crush a car like a tin can. The temperature sits near freezing. Animals here have had to develop entirely new strategies just to survive. Some make their own light. Some have no eyes. Some have mouths bigger than their bodies. Then below 13,000 feet, you reach the abyss, a world so extreme that even deep-sea researchers describe it as barely explored, a place where the pressure exceeds 1,000 times what you feel standing on a beach. Now here is the thing about sperm whales. They skip through the first 3 layers almost without stopping. They surface to breathe, tip their bodies at a steep angle, and sink. They pass the bright zone, they pass the twilight zone, they pass the dark zone entirely, and on their deepest recorded dives, they push into the upper edge of the abyss itself. A routine hunting dive takes them to around 2,000 feet. That puts them solidly in complete darkness, below any useful light, in a world most animals never enter. Researchers tracking sperm whales with depth recorders watched this happen over and over and found something telling. The whales spend almost no time in the upper layers during a dive. They drop through those zones like they are just passing through a hallway, trying to reach the room at the end. The room at the end is where the food is. Specifically, squid. Large, fast, strange-looking squid that live in the mid to deep water column and avoid the bright surface zones entirely. The sperm whale evolved its entire body around chasing animals that live in a place most creatures treat as a death zone. So when people ask why sperm whales go so deep, the answer is simple. That is where dinner is. And dinner can be very, very hard to catch. The whale uses its sonar to scan the darkness as it descends, building a picture of what is ahead. Shapes appear in the echo. Something moves. The whale adjusts. What it is tracking, what it finds down there in the middle of that crushing black silence, is bigger and stranger than you might expect. And the first time scientists got a real look at it, they were not fully prepared for what they saw. 2,000 feet below the surface, there is no color. There is no shape. There is nothing your eyes can detect at all, because light from the sun runs out completely around 600 feet down. By 2,000 feet, you are in a world that has never once been touched by sunlight. Try to picture it. You are in a space the size of an ocean, and every direction looks identical. Up, down, left, right. All black. The kind of black that does not adjust to. The kind where opening and closing your eyes makes no difference. The temperature here hovers just above freezing, not the sharp cold of a winter morning. A slow, total cold that surrounds everything evenly, like being inside a refrigerator with no shelves and no walls. The pressure is the other thing. At 2,000 feet, the water above you weighs about 60 times what the air above your head weighs right now. Every square inch of surface area on your body would be absorbing that weight simultaneously. For a human, that would be instantly fatal. The lungs would collapse, the sinuses would crush inward, the body has nowhere to push back. A sperm whale handles this differently, and we will cover exactly how later. But for now, understand the environment as what it is. An extreme place, a hostile place, a place designed by physics to kill most things that enter it. And yet, life is everywhere down there. That is one of the most counterintuitive things scientists have found about the deep ocean. You would expect a cold, dark, crushing environment to be nearly empty, barren, a wasteland. Instead, researchers who have sent cameras into that depth find movement constantly, things passing through the frame, things that glow, things that drift slowly until something disturbs them and then vanish at speed. The deep ocean is teeming with animals, many of which we still have not formally described or named. The darkness creates its own rules. Animals that live down there do not chase each other through open water the way surface predators do. They wait. They ambush. They have evolved over millions of years to be patient, because in the dark, patience beats speed most of the time. Some animals hang in place for hours, waiting for something to swim into range. Then they strike. The whole hunt happens in total silence and total darkness, measured in seconds. Now add a sperm whale to that environment, a 52-foot animal descending at speed, clicking rapidly, building a sound map of everything around it. The clicks travel outward, bounce off prey animals, and return. The whale reads those echoes with extraordinary accuracy, tracking position, size, and movement in real time. From the prey's perspective, the arrival of a sperm whale is like a sonar ping coming out of nowhere in the dark. Some animals flee, some freeze, some, it turns out, fight back. And that is where the story starts to change, because the deeper the whale goes, and the bigger the prey it finds, the more the darkness stops being the whale's advantage alone. The things that evolve to live in permanent darkness are built specifically for this environment. The whale is visiting. They live there, and what some of those animals can do in the dark is going to be the focus of what comes next. A sperm whale begins its hunt before it even reaches its prey. As it descends through the dark water, it produces a rapid series of clicks. Each click lasts less than 1 millisecond, but the sound travels far and bounces back with information. The whale collects those returning echoes through its lower jaw, which acts as a receiver and channels sound directly toward the inner ear. The result is a three-dimensional picture of the water ahead. Distance, size, shape, movement, all of it constructed from sound in a place where eyes would be completely useless. Scientists who have studied this call it biosonar, and sperm whale biosonar is among the loudest and most powerful biological sound systems on the planet. The clicks a sperm whale produces can reach 230 decibels. To put that in perspective, a jet engine at full throttle sits around 140. A sperm whale's click, measured up close, is louder than almost anything a living creature can produce. That power matters at depth. Sound travels faster and farther in cold, dense water. The whale's clicks can reach targets hundreds of feet away and still return clearly enough to read. In a world with no light, this is the equivalent of seeing with stadium-level floodlights. As the whale gets closer to its target, the pattern of clicks changes. The clicks speed up, forming what researchers call a creak, because the rapid-fire sequence sounds a bit like a door hinge squeaking. Scientists learn to identify this creak sound as the moment of attack. The whale is narrowing in. It is almost at striking range. The creak is the hunting mode activating. Then there is a moment of silence. The whale is right on top of its prey. What happens in that silence is something researchers have only partially pieced together. The whale is in total darkness, moving at depth, aiming a mouth full of large gripping teeth at a fast-moving animal that can change direction instantly. Squid in particular are fast. They move by jet propulsion, pulling water in and expelling it in controlled bursts. A squid can accelerate from a dead stop to full speed in a fraction of a second. Even with perfect sonar, catching one in open water requires precision that seems almost impossible from the outside. And yet sperm whale stomachs, when examined by researchers, are regularly packed with squid, hundreds of them at a time. The hunt works. Somehow, in total darkness, in freezing water, under 60 times the pressure of the surface, this animal catches fast prey efficiently enough to fuel a 45-ton body. A whale that size needs to eat roughly 1.5 tons of food per day just to maintain itself. 1.5 tons every day. Hunted in the dark. That number alone should recalibrate how you think about these animals. They are not occasional hunters poking around the deep out of curiosity. They are full-time, high-efficiency predators operating in one of the most hostile environments on Earth. But efficient does not mean easy. And the prey does not always cooperate. Sometimes the prey is large enough to make the hunt a genuine contest, large enough to fight back, large enough to leave marks that last a lifetime. And that brings us back to the scars and to the specific animal responsible for most of them. Inside a sperm whale's head, something remarkable is happening on every dive. The whale produces its clicks using a pair of structures near the front of its skull called the monkey lips. These are dense, rubbery folds of tissue that slam together under muscular pressure, generating a pulse of sound. That pulse travels backward through the spermaceti organ, a large cavity filled with waxy oil that the whale uses to focus and aim the sound forward through the water. The oil in the spermaceti organ changes density depending on temperature. The whale can actually regulate the temperature of the oil slightly by controlling blood flow to the area, which lets it fine-tune the focus of the beam. This is a biological lens built from liquid wax and blood circulation. That level of control is extraordinary. The whale is not just firing clicks randomly, it is shaping the beam, focusing it, adjusting its direction the way a flashlight's reflector dish shapes a beam of light. The returning echoes come back through the lower jaw. The jawbone is hollow in places and filled with a fatty tissue that conducts sound efficiently directly toward the inner ear. The whole system, from click generation to echo reception, is one continuous biological machine. Now here is what makes this genuinely strange. The clicks a sperm whale produces are so loud at close range that researchers believe they may be capable of stunning or even disorienting prey on contact. At 230 decibels, the sound pulse is powerful enough to cause physical effects in tissue at short range. No one has directly filmed a sperm whale using sound as a weapon in the wild, but the biology makes it plausible, and some researchers take it seriously. If the whale can aim that beam with precision, it has the option of concentrating it on a target at close range before the physical grab. The clicks also serve a second function: communication. Sperm whales produce specific patterns of clicks called coders, and different groups of whales use different coders the way different regions have different dialects. A whale from the Pacific uses a different coder pattern than a whale from the Atlantic. Those patterns are learned, passed from mothers to calves, and maintained across generations. Scientists studying this have described it as a form of culture. Sperm whales carry learned traditions. They inherit their click dialects the way humans inherit language. That adds a layer to everything else happening during a hunt. When a whale descends into the dark and begins clicking, it is doing at least two things at once: scanning the environment for prey and potentially communicating with other whales in the group, sharing information about what it is finding below. Researchers have recorded what sounds like coordinated dive behavior in sperm whale groups. The whales do not all descend together, but their timing and surface behavior suggests some level of information sharing about where prey is concentrated. So the hunt in the dark is not necessarily a solo operation. It may be organized, it may be strategic. The clicking system may be carrying more information than just an echo of a squid. And if sperm whales coordinate their hunts with sound, the picture of what they encounter below becomes more complicated, because what they are hunting is also capable of coordinated movement. It is also fast, also intelligent after a fashion, and also fighting for its life in the same darkness. What that prey can actually do is something most people have never fully appreciated. Stand a sperm whale upright, and its head would reach the 4th floor of a building. The head is rectangular, blunt at the front, and almost comically large compared to the rest of the body. From a design standpoint, it looks like a mistake. From an engineering standpoint, it is the most sophisticated biological structure in the ocean. The spermaceti organ alone, the large wax-filled cavity that dominates the interior of the head, can hold over 500 gallons of oil. Whalers in the 1800s and 1900s hunted sperm whales almost entirely for this oil, which burned cleanly in lamps and was used as lubricant for fine machinery. A single whale could produce enough spermaceti to fill an entire room with liquid, but the oil was always secondary to what it actually does for the whale. At depth, the spermaceti organ serves as a buoyancy control device. When the whale wants to sink quickly, it can cool the oil by letting cold seawater flow through special channels in the nasal passages. Cooler oil becomes denser. Denser oil is heavier. The head becomes heavier. The whale sinks faster without burning extra energy. When it wants to rise, it reverses the process. Warm blood from the body heats the oil back up. It becomes less dense. The head lightens. Ascent becomes easier. This is a self-regulating ballast system built out of biological oil. The whale is not swimming down and fighting its own buoyancy the whole way. It is using physics adjusting the density of the material in its own head to manage its position in the water column. That frees up enormous energy for the actual hunt. The head is also a ram. Historically, sailors described incidents of large male sperm whales charging ships at speed and striking the hull head-on. The most famous case involved a whaling ship in the early 1800s that was struck twice by a large bull and sank in the middle of the Pacific Ocean. The crew survived, and the story became the basis for a novel many people know. The whale that struck that ship was estimated at 85 feet by some accounts, well beyond any confirmed modern size. But the behavior of ramming with the head has been recorded in more recent encounters as well. The blunt, dense, oil-filled head is structurally reinforced to absorb the impact of a collision. The bones around the front of the skull are thick. The spermaceti organ itself cushions the internal structures. The whole front of the animal is built to hit something hard without damage to itself. So the head is simultaneously a sonar emitter, a buoyancy controller, and a battering ram. 3 functions, 1 structure, and then consider the brain inside it. A sperm whale brain can weigh up to 20 pounds, 5 times heavier than a human brain. The sections responsible for processing sound are massively developed. The sections linked to social behavior and long-term memory are large as well. This animal remembers, it communicates, it coordinates, and it can hit things with its face hard enough to sink a wooden ship. What that head is built to hunt in the dark below is something that, until recently, most humans had only ever seen washed ashore, dead and pale, carried out of the deep by a sperm whale's stomach. For most of human history, no one knew what sperm whales did underwater. The surface was observable, the deep was not. Whalers studied the animals they killed and found strange things inside the stomachs. Hard, sharp, indigestible objects. Beaks, shaped like a parrot's beak but much larger. Dozens of them, sometimes hundreds. Those beaks did not belong to any bird. They came from squid, and the size of some of them suggested the squid they came from were enormous. That was the first clue. Whalers did not understand exactly what it meant, but they logged it. The whales were eating something big, something that had a sharp, hard beak the size of a man's fist. The second clue was on the outside of the whales. When whalers processed sperm whales, they documented the skin. The circular scar patterns appeared consistently on large adults. Round marks in clusters, sometimes dozens on a single animal. The whalers connected these marks to the squid beaks in the stomachs. Something with sucker rings was fighting back during the hunt. The third clue came from ambergris. Ambergris is a waxy substance that forms in the intestines of sperm whales, and for centuries it was used in perfume production. Because of its unusual properties, when scientists examined ambergris closely, they found squid beaks embedded throughout it. The beaks were indigestible. The whale's gut wrapped them in layers of waxy material over time, the way an oyster builds a pearl around an irritant. The sheer volume of beaks found in ambergris samples suggested some whales swallowed squid by the hundreds. The scale of the hunting was hard to picture. Modern researchers pushed further. They developed satellite tags small enough to attach to whale skin, equipped with depth sensors and hydrophones that could record sound. A whale tagged this way became a data point. Every dive logged, every click recorded. Researchers could reconstruct the dive profile, the depth, the duration, the acoustic pattern. What those tags showed was consistent with what the old whalers had documented, but far more precise. The whales dove deep, clicked rapidly, went into creek mode repeatedly, then returned to the surface. The creek sequences indicated active attacks, multiple attacks per dive. The whales were not just descending and wandering, they were hunting aggressively, repeatedly, every time they went down. Then came the rare visual evidence. Underwater camera systems managed to capture footage of sperm whale interactions at depth in a small number of cases. What the footage showed was an animal moving with surprising speed and direction changes for something its size, clearly chasing something. The prey itself was rarely visible, but the whale's behavior told the story, and in one category of evidence, the truth became undeniable. When whales were found dead and their stomachs opened by researchers, the beaks inside were matched to species. Giant squid, animals that can reach lengths of 40 feet, including tentacles. Some beak sizes pointed to individuals larger than any squid ever brought to the surface intact. Something down there was big enough to leave beaks that size. And whatever it was, the sperm whale was willing to fight it, every single day. The scars were proof the fights were real. What was still missing was proof of exactly what the whale was fighting. That answer was closer than anyone expected, and it was stranger than most people were ready for. The scars on a sperm whale are a record, a physical archive of every fight the animal has survived, and scientists have learned to read them. The most common pattern is a ring of circular marks arranged in a cluster. Each mark is a sucker impression, left by the arm or tentacle of a squid, pressing against the whale's skin with enough force to leave a permanent scar. On some whales, the marks are small, consistent with smaller squid species. On others, the rings are as wide as a dinner plate. Dinner plate-sized sucker marks on the skin of a 52-foot whale. That measurement alone tells you something important about the size of the animal producing those marks. Squid suckers are proportional to the animal's body. A small squid has small suckers. A large squid has large suckers. Some species of large squid also have hooks, hard curved structures that rim the sucker and dig in when the arm grips. Those hooks leave a different kind of mark, a crescent-shaped cut rather than a clean circle. Both types have been documented on sperm whale skin. The location of the scars also carries information. Marks concentrated around the head and jaw area suggest the squid was fighting near the whale's mouth during or after capture. Marks spread along the body suggest longer contact, possibly a struggle that extended beyond the initial grab. Some whales carry old, faded scar clusters alongside fresh ones, showing that the same animal has been through multiple serious encounters across its lifetime. Researchers have used the size and distribution of these scars to make estimates about the squid responsible. By measuring the diameter of the sucker marks and comparing them to known squid anatomy, scientists can work backward to estimate body size. Those estimates have produced numbers that are uncomfortable to sit with. Some of the largest sucker impressions recorded on sperm whale skin correspond to squid with bodies potentially reaching 10 feet or more in mantle length, meaning the total animal, including tentacles, could extend to 30 or 40 feet. An animal roughly the length of a school bus, meeting a whale in total darkness, 2,000 feet below the surface. And the whale has the scars to prove the meeting happened. What is harder to determine from scars alone is the outcome of each individual encounter. Most encounters clearly end with the whale winning, given that squid beaks fill whale stomachs consistently. The whale eats and survives. The scar is a trophy of a successful hunt that got physical. But researchers have noted that some whales carry scar patterns severe enough to suggest the struggle was significant. Broad, overlapping impressions across large areas of skin, multiple hook cuts in clusters, evidence of gripping at different angles, as if the squid repositioned during the fight. That kind of evidence points to a prey animal that did not simply accept its fate. It fought. It grabbed. It tried to turn the encounter in its favor. The whale was stronger. The whale carries the evidence on its skin for the rest of its life. And the deeper the whale goes, the larger the squid it encounters. The deepest dives correspond to the largest prey. That relationship between depth and scale is what has led researchers to ask a question that gets stranger the more seriously you take it. If the scars from 2,000 feet look like this, what do the animals living twice as deep look like? For centuries, the giant squid existed in rumor. Sailors described sea monsters with arms as long as ship masts, creatures that rose from the deep and dragged boats down. The stories were exaggerated, but they were built on something real. The giant squid is real. It is enormous. And until recently, almost no one had ever seen a living one. Scientists call it by its scientific name, but most researchers simply say giant squid. Confirmed specimens have been measured at lengths of around 40 feet from the tip of the mantle to the end of the longest tentacles. The mantle alone, the main body tube, can reach 6 feet in length. The eyes are the largest of any animal on Earth, up to 10 inches in diameter, roughly the size of a dinner plate. Those eyes evolved specifically to detect the faint bioluminescent flashes produced by sperm whales moving through deep water. The arms number 8, and then there are 2 longer tentacles that shoot out to capture prey. The tentacles on a full-grown giant squid can extend over 30 feet. They move fast. They grip hard. The suckers along the arms carry sharp, serrated edges on some specimens, capable of cutting into flesh during a struggle. Finding them alive is nearly impossible. Giant squid live in the deep mid-water column, somewhere between 1,000 and 3,000 feet in most estimates. They do not come to the surface willingly. They die quickly in shallow water or when brought up in nets. Most of what scientists knew about them, for most of the 20th century, came from dead or dying specimens that washed ashore or were hauled up accidentally. The first confirmed photographs of a living giant squid in its natural habitat were taken in the early 2000s by a Japanese research team. They lowered a camera rig with bait to about 3,000 feet and waited. Eventually, something took the bait. The resulting images showed an animal over 20 feet long, moving with speed and aggression that surprised the researchers watching the footage. That footage changed how scientists thought about the giant squid. Before it, the assumption was that the animal was a slow drifter, passively floating at depth and waiting for food to come to it. The footage showed something different, an active hunter, an animal with muscle and speed, reacting quickly and powerfully, which reframes the sperm whale hunt completely. The whale is descending into the territory of an animal with 10-inch eyes, 30-foot tentacles, serrated suckers, and documented aggression. An animal that can see the whale coming before the whale even clicks its way into striking range. Scientists believe the giant squid's massive eyes evolved in direct response to sperm whale predation. An eye that large can detect the faint blue glow of a whale's bioluminescent wake from a considerable distance in the dark. The squid may see the whale coming and decide whether to flee or fight. Sometimes it flees. Sometimes, based on the scar evidence, it does not. And the giant squid is only one of the large cephalopods a sperm whale regularly encounters. There is another species, heavier and arguably stranger, that lives even deeper and makes the giant squid look almost manageable by comparison. No human has ever directly watched a full sperm whale versus giant squid encounter in the wild. The depth, the darkness, and the speed of the event make direct observation nearly impossible with current technology. But scientists have reconstructed what likely happens using behavioral data, acoustic recordings, stomach contents, and the scar record. Here is the picture they have built. The whale descends through the dark, clicking steadily. The echo returns tell it what is ahead. Somewhere around 2,000 feet, the sonar picks up something large. The clicks intensify. The whale angles toward the target. The squid, with its enormous eyes, may detect the faint bioluminescence disturbed by the whale's movement before the whale is in click range. Or it detects the clicks themselves, vibrations moving through the water. Either way, it has a window of reaction time. If the squid tries to flee, it fires its jet propulsion and accelerates. The whale adjusts course and follows the echo. The clicks are now in creek mode, rapid fire, tracking a moving target at close range. The whale is close, very close. The strike happens in the dark. The whale opens its narrow jaw and grabs the teeth close around part of the squid's body. The squid's arms immediately respond, wrapping around whatever surface they can reach. On a sperm whale, that means the head, the jaw, the area around the eyes, the arms pull, the suckers press. If the squid has hooks, they dig in. The whale has to hold on and swallow while the squid is actively fighting to escape. The strength involved on both sides is difficult to picture. The whale weighs up to 45 tons. The squid's mantle muscles can generate forces strong enough to fracture their own gladius, the internal shell structure, if they contract too hard under stress. The fight lasts seconds to perhaps a minute or two. Then, it is over. The whale swallows. The squid is gone. The whale clicks its way back into hunting mode. The scar left behind on the whale's skin is the only lasting record of what happened. But sometimes the encounter does not go cleanly. Sometimes the squid is large enough, or the angle is wrong, or the whale misses the first grab, and the squid wraps its tentacles around the whale's jaw, blocking the bite. Researchers have found evidence of squid arms lodged in whale throats, evidence of multiple squid consumed in sequence on a single dive, which suggests the whale learns the location of squid clusters and works through them methodically. They have also found evidence of something more uncomfortable. Some whales showed jaw deformities, crooked or partially paralyzed jaws that scientists attribute to old injuries. A jaw that was grabbed hard enough or twisted at the wrong moment and healed at an angle. An animal the size of a city bus with a damaged jaw from a fight in the dark. That is the reality of what the sperm whale faces every single day beneath the surface. And what makes this stranger is that the animal it is fighting in this scenario, the giant squid, is not even the heaviest cephalopod in the ocean. There is another one, heavier, wider, equipped differently, and it lives deeper. Most people have heard of the giant squid. Fewer people know about the colossal squid, and the difference between the two matters a great deal when you are trying to understand what sperm whales actually encounter at depth. Giant squid and colossal squid are separate species. They look similar at first glance, both large, both with 8 arms and 2 long tentacles, both living in the deep ocean. But in terms of mass, the colossal squid wins by a considerable margin. Giant squid reach greater lengths. Their long tentacles can stretch the total body measurement to around 40 feet, but they are relatively lean animals, built for speed and reach. Colossal squid are shorter in total length but far heavier. A confirmed specimen caught by a New Zealand fishing vessel in the Southern Ocean years ago weighed over 1,000 pounds and measured around 15 feet in mantle length alone. Scientists estimated the full length, including tentacles, at somewhere between 30 and 33 feet. The mass of that animal was nearly twice what a giant squid of similar tentacle length would weigh. The colossal squid also has a different weapon system. Instead of serrated sucker edges, it carries rotating hooks on its tentacle clubs. These hooks can spin, allowing the tentacle to grip and tear simultaneously. The physical damage a colossal squid can inflict during a struggle is different from, and potentially worse than, what a giant squid produces. The colossal squid lives primarily in the waters around Antarctica and in the deep Southern Ocean. Sperm whales range into those same waters, and Antarctic sperm whale populations show scar patterns consistent with colossal squid encounters. Some of those scar marks are larger than anything attributable to giant squid, suggesting the colossal squid is an active player in the whale's deep-sea hunt. Here is what makes the comparison genuinely striking. Colossal squid eyes have been measured at 16 inches in diameter on adult specimens. 16 inches. An eye wider than a dinner plate evolved to function in near-total darkness. That eye detects bioluminescence, pressure changes, and possibly the sonar clicks of approaching sperm whales. An animal with a 16-inch eye, rotating hooks on its tentacles, and a body mass of over 1,000 pounds, and the sperm whale hunts it. Both squid species represent what the deep ocean does to animals over millions of years of evolution. The pressure, the darkness, the competition for resources in a world without sunlight pushes animals toward extreme body plans. Size becomes an advantage. Reach becomes critical. Weapons get specialized for specific kinds of encounters. The squid did not grow to these sizes by accident. They grew to these sizes partly because something very large was hunting them, and only the biggest, fastest, most defensible individuals survived long enough to reproduce. The sperm whale and the giant squid shaped each other, an evolutionary arms race running in the dark for millions of years, which means both animals are still changing, still competing. And the current version of that contest is happening right now, every day, in the deep ocean beneath your feet. There is something both unsettling and extraordinary about that. Two massive animals locked in a biological contest that predates humanity by millions of years, playing out in a place most humans will never see. But the squid is not the only danger a sperm whale faces at depth. The environment itself has its own ways of killing things that enter it. At 10,000 feet below the surface, the pressure of the ocean above you is roughly 300 times the pressure you feel standing on land right now. Put a styrofoam cup at that depth, and it comes back the size of a thimble, every air pocket compressed out of it by sheer force. Put an unprotected human at that depth, and the result is instantaneous and total. The pressure at 10,000 feet does not feel like being squeezed from outside. It feels like everything inside you being pushed toward the middle, simultaneously. Air spaces in the body, sinuses, lungs, the middle ear, all of them collapse inward under the weight of the water above. There is no gradual adjustment. Below a certain depth, the physics simply overwhelm biology. For most animals, this is an absolute limit. The deep ocean below a few hundred feet is simply unreachable without mechanical protection. Sperm whales reach 10,000 feet and survive. On their deepest recorded dives, they go there and come back intact. How they manage this is one of the more remarkable biological stories in the animal kingdom. The key is what the whale does with its lungs. As it descends, the increasing pressure compresses the air in the lungs progressively. Rather than holding the lungs rigid and fighting the compression the way a pressurized submarine hull does, the whale lets them collapse. The lungs are flexible enough to fold inward as the pressure increases. The ribs can flex, the chest wall moves. By the time the whale reaches extreme depth, its lungs have compressed to a fraction of their surface volume. The air that was in them has shifted into the upper airways, and the trachea, where it is protected from the nitrogen absorption effects that cause decompression sickness in human divers. Decompression sickness happens when a diver breathes compressed air at depth. The nitrogen in that air dissolves into the bloodstream under pressure, and when the diver ascends too quickly, it comes back out of solution as bubbles inside the tissue. The bubbles cause joint pain, neurological damage, and in severe cases, death. It is called the bends. Sperm whales mostly avoid this because their lung collapse prevents prolonged breathing of compressed air. The gas exchange stops when the lungs fold. The nitrogen cannot load into the blood in the same way. The whale is essentially running on the oxygen already stored in its blood and muscle tissue, rather than continuously breathing at depth. That oxygen store is extraordinary. Sperm whale blood carries oxygen at densities that dwarf what human blood can manage. The muscle tissue itself is so packed with oxygen-binding proteins that it looks nearly black rather than red. When you see sperm whale muscle tissue, the color alone tells you how much oxygen it holds. 10,000 feet, collapsed lungs, black muscle, and a body navigating total darkness on a stored oxygen budget. The margin for error at that depth is narrow. Every extra minute costs oxygen the whale cannot replace until it surfaces. Every extra second spent chasing prey that evades the first strike is a second the whale cannot get back, which raises a question that researchers have spent considerable effort trying to answer. What happens when a sperm whale pushes too far? The lung collapse a sperm whale undergoes on a deep dive is controlled, deliberate, built into the physiology over millions of years of evolution. Understanding it requires thinking about the body as a system designed around a specific trade-off: oxygen access at the surface, oxygen conservation at depth. When a sperm whale surfaces after a dive, It breathes through its single blowhole, which sits off-center on the left side of the head. The blow shoots upward and slightly forward, and it is visible from a considerable distance. The whale breathes multiple times at the surface, loading oxygen into blood and muscle tissue. Researchers watching tagged whales have documented how many breaths a whale takes before descending again, and how that number changes based on how deep the previous dive was. On average, a whale rests at the surface for about 8 to 10 minutes between deep dives. During that time, it is not just resting, it is replenishing. Then it angles down. The body is dense enough that it requires active swimming to descend initially, but at a certain depth, the compressed lungs reduce the whale's overall buoyancy enough that it becomes negatively buoyant. It starts to sink. The whale can then reduce its active swimming and glide downward, conserving energy. As the descent continues, the ribcage flexes inward, the diaphragm shifts, the lungs compress progressively, and the air inside them moves toward the upper airways where it stays protected. The whale's body handles this structurally because the ribcage is not rigidly fixed the way a human ribcage is. The ribs articulate more freely, allowing the chest wall to move inward without structural damage. At depth, the whale is running on what it stored at the surface: oxygen bound to hemoglobin in the blood, oxygen stored in myoglobin in the muscle tissue. The muscles in particular carry an enormous reserve. The darker the muscle, the more myoglobin it contains, and sperm whale muscle is as dark as liver. The whale also has a cardiovascular response called a dive reflex, shared in less extreme forms with other marine mammals, and even with humans to a small degree. During the dive, the heart rate slows significantly. Blood flow to the extremities is reduced. The core, including the brain and heart, gets priority. The peripheral muscles receive less circulation. This is the whale essentially rationing, directing its limited oxygen supply to where it matters most, and letting the extremities run on lower levels until the whale surfaces again. The whole system is elegant. It is also a countdown. Every moment at depth is consuming reserves that only surface air can replenish, and there is a component that varies between individuals. Some whales have larger oxygen stores than others, larger spleens, which act as reserve tanks of red blood cells released into circulation at the start of a dive. Younger whales have smaller oxygen reserves and dive less deep. As whales age and grow, the reserve expands. A mature adult male can manage what a juvenile cannot. That difference in dive capacity corresponds directly to a difference in what prey those animals can access. The deepest, heaviest squid live below what a juvenile whale can reach. Only the largest adults regularly push into those depth ranges, which means the oldest, most experienced whales are the ones facing the biggest prey. And the biggest prey waits at a depth where the margin for error is smallest. What happens if the margin runs out is not something the whale can negotiate. The deep does not offer second chances. A sperm whale cannot check a watch. It cannot read a depth gauge. It cannot calculate how much oxygen it has left by looking at a meter on the wall, and yet it manages its dive duration with a precision that keeps it alive across a lifetime of dives into extreme conditions. The mechanism is biological, but the outcome functions almost like a timer, and understanding it changes how you see every moment of a sperm whale's time below the surface. The signals start in the muscle tissue and blood. As oxygen levels drop during a dive, the chemistry of the blood shifts. Carbon dioxide builds up. Lactic acid from muscle activity accumulates. The brain monitors these signals continuously, and as they reach certain thresholds, the drive to return to the surface becomes powerful and increasingly urgent. This is the same mechanism that makes humans feel the need to breathe when they hold their breath underwater. It is primarily the rising carbon dioxide level, not the falling oxygen level, that triggers the urge. But in sperm whales, the thresholds are calibrated very differently. They can tolerate much higher CO2 levels and much lower oxygen levels before the urgency to surface becomes irresistible. Scientists have modeled these thresholds using data from tagged whales and direct physiological measurements from stranded animals. The models suggest a sperm whale can manage roughly 45 minutes on a routine dive at around 2,000 feet before the physiological pressure to return becomes dominant. On deeper dives, the math changes. At greater depths, the whale is burning oxygen faster because it is swimming harder, dealing with colder water, and potentially engaged in more active hunting behavior. The timer runs down faster. The margin for a long hunt at 10,000 feet is much tighter than the margin at 2,000 feet. Researchers have also noted that experienced adult whales seem to optimize their behavior at depth in ways that extend the dive. They slow their movements during gliding phases. They time their attacks to minimize wasted energy. They surface on a trajectory that balances speed against oxygen cost. This optimization is learned. Young whales are less efficient. Their dives are shorter, less deep, and less productive. Older whales dive better, hunt better, and manage the oxygen budget better. The skill accumulates over decades. Sperm whales can live into their 70s. By the time a male reaches full size and is making his deepest dives, he has been practicing for 30 or 40 years. That accumulated experience shapes every hunt. The whale is not guessing. It has a refined biological sense of its own limits, developed across thousands of dives. And even with all that experience, the deep is still dangerous. The prey does not cooperate. A hunt that runs longer than planned, a squid that fights for an extra minute, a swim in the wrong direction, any of these can compress the remaining margin. What the whale does in those final moments before it must surface, how it decides to break off a hunt and rise, is something researchers have only partially mapped. The acoustic record shows whales going silent and beginning the ascent before the clicks stop entirely, suggesting a decision point rather than a simple shutdown. The whale chooses to come up, and yet some whales do not come up when they should. Some push the margin too far. What happens in those cases is one of the darker chapters in sperm whale biology, and it helps explain why the deep is genuinely lethal even for an animal built specifically for it. The consequences of running out of oxygen at depth are severe for any air-breathing animal. For a sperm whale, the situation is complicated by its size, its depth, and the biology of its specific adaptations. If a whale's oxygen reserves fall critically low during a dive, the first systems to fail are the ones the dive reflex has already partially shut down. The peripheral muscles begin to lose function. Coordination becomes impaired. The whale may struggle to maintain direction or generate the propulsive force needed to ascend quickly. Below 2,000 feet, a whale that cannot swim upward efficiently is in serious trouble. The pressure at that depth means the whale is still negatively buoyant unless it is ascending and actively swimming. A whale that loses meaningful muscle function at depth will sink further rather than rise. This scenario plays out in the physiological record. Some stranded sperm whales found on beaches show signs of decompression injury despite the whale's adaptations. The adaptations are extraordinarily effective, but they are not absolute. Under unusual circumstances, specifically very deep dives, extended hunts, or repeated deep dives with insufficient surface recovery time, the protective mechanisms can be pushed past their limits. Decompression injury in sperm whales has been documented in post-mortem examinations of stranded animals. Gas bubbles in tissue, lesions consistent with nitrogen coming out of solution too quickly, evidence that the ascent was faster than the whale's physiology could safely manage, possibly because the whale had already stayed too long and was in physiological distress. Researchers have also pointed to human-generated noise as a factor. Military sonar operating at certain frequencies has been associated with mass strandings of deep-diving whales in multiple incidents. The working theory is that the noise startles the animals and triggers a rapid ascent that bypasses the careful decompression management their bodies normally perform. The result is decompression injury from ascending too fast from too deep. In that scenario, the threat does not come from below, it comes from above, from sound traveling down through the water and disrupting the precise biological management that keeps the whale alive during its return to the surface. Beyond decompression, there is the risk of what researchers call shallow water blackout in reverse. Standard shallow water blackout happens to human divers who hyperventilate before a breath-hold dive. The oxygen level drops critically low during the ascent near the surface when the pressure reduction causes a sudden drop in blood oxygen partial pressure. Consciousness goes without warning. In sperm whales, the equivalent scenario is less well understood, but potentially real. A whale running very low on oxygen during a long ascent from extreme depth might experience a critical oxygen drop near the surface precisely when it is closest to safety. There is no rescue at that depth. The whale either makes it to the surface or it does not. The ones that do not are never seen again. They sink. They disappear into the same deep water that made them what they are. What waits for them at the bottom and what lives down there permanently belongs to a completely different category of existence. A place where the rules of the surface do not apply, and where even the concept of a food web looks nothing like what we normally picture. Below the depth sperm whales regularly reach, the ocean continues, and what it becomes is something that challenges most people's sense of what life actually requires to exist. The abyssal zone begins at around 10,000 feet and extends to roughly 21,000 feet. The pressure at the deepest points exceeds 1,000 times the pressure at sea level. The temperature sits between 2 and 4 degrees above freezing across most of its area. The seafloor in the abyss is largely flat, covered in fine sediment that has been accumulating, layer by layer, for millions of years. By every measure that seems necessary for life on the surface, the abyss should be empty. Scientists who first sent cameras into the abyssal zone expected something close to a desert, cold, dark, featureless, and mostly barren. What they found was a populated world. The abyss holds life that looks like nothing most people have encountered outside of deep-sea documentaries. Creatures with bodies translucent as glass, animals that produce their own light through chemical reactions in their tissue, fish with teeth proportionally so large their mouths cannot fully close, worms longer than a person, creatures that are technically animals but move so slowly they are almost indistinguishable from the sediment they live on. The food web here runs on what falls from above. Scientists call it marine snow. It is a constant drift of organic material from the upper ocean, fragments of dead organisms, fecal matter, shed skin, the remains of surface life sinking slowly through the water column. By the time it reaches the abyss, it is nutritionally sparse. The animals that evolved to live here are extraordinarily efficient at extracting energy from it. Some abyssal creatures can go weeks or months without a significant meal. Their metabolisms have slowed to a fraction of what surface animals maintain. Time operates differently in the abyss, in a biological sense. Growth is slow, reproduction is infrequent, lifespans in some species extend for decades or centuries. The Greenland shark, which reaches the upper edge of abyssal depths in some regions, has been aged at over 400 years in recent studies. It grows less than half an inch per year. Its world operates on a timescale that makes the surface seem frantic by comparison. Now consider what a sperm whale's deepest dives mean in this context. When an adult male pushes past 10,000 feet, it is entering the abyssal zone, an air-breathing surface animal reaching down into a world that runs on entirely different rules. A visitor in a place where the permanent residents have adapted over millions of years to conditions that the whale can only tolerate for minutes. What lives at those depths that the whale might encounter is largely unknown. The abyssal zone remains one of the least explored places on the planet. Scientists estimate that less than 20% of the deep-sea floor has been mapped in any meaningful detail. The animals living in the mid-water column of the abyss, the zone the whale passes through on its deepest dives, are even less documented than the seafloor itself. Something down there evolved those enormous sucker marks on the whale's skin. Something at the boundary of the abyssal zone is big enough strong enough, and aggressive enough to leave lasting scars on the largest toothed predator alive. And we still do not know exactly what it is. What we do know is that the abyss is alive, densely, strangely, extraordinarily alive. And it gets stranger the deeper you go. The deep ocean is dark, but it is not completely black. Walk through the abyss and you would see flashes, pulses of blue and green light appearing and vanishing in seconds, a streak of cold fire across the dark water as something large moves through it, a slow, steady glow drifting downward from above. The deep ocean produces its own light, and it does so constantly, in every direction, at almost every depth below the sunlit zone. Scientists estimate that somewhere between 76 and 80% of deep-sea animals produce bioluminescence. That number is staggering. In the deep ocean, making light is the rule, not the exception. The chemistry behind it is the same basic reaction across most species. A molecule called luciferin reacts with oxygen in the presence of an enzyme, and the result is a photon of light with almost no heat. Cold light, produced on demand by living tissue in colors tuned specifically to travel through deep seawater efficiently. Blue travels farthest in cold, deep water. Most deep-sea bioluminescence is blue or blue-green. For exactly that reason, the animals that evolved to produce it also evolved eyes tuned to detect it. The whole system is built around the physics of that specific color in that specific environment. The uses of bioluminescence vary wildly depending on the animal. Some use it to attract prey. The anglerfish is the famous example, a fish with a glowing lure dangling from its head that attracts smaller animals into striking range. But the anglerfish is far from alone. Many deep-sea predators use light as a trap in some form, mimicking the bioluminescence of small prey to draw larger animals close enough to attack. Some use it for camouflage. Counter-illumination is a strategy where an animal produces light on its underside to match the faint light filtering down from above, making itself invisible to predators looking up from below. The animal becomes part of the background. Some use it for communication. Certain squid species produce complex, rapidly changing light patterns across their skin that researchers believe function as signals to other individuals of the same species. In total darkness, a flashing pattern visible from 30 feet away is a powerful communication tool. And some use it accidentally in a way that turns out to be a serious problem. When something large moves through bioluminescent water, the disturbance triggers the organisms in the water to flash. The wake of a large animal passing through the deep leaves a trail of light behind it. Trails visible to anything with eyes sensitive enough to detect them. A sperm whale moving through bioluminescent water leaves a glowing wake. The whale's own sonar system is extraordinarily powerful, but in a world where its passage lights up the organisms around it, the whale announces itself to every animal in the area with eyes large enough to see the glow. Giant squid with 10-inch eyes, colossal squid with 16-inch eyes, both built specifically to detect bioluminescence at long range in dark water. The whale may detect the squid with sound before the squid detects the whale with light, or the squid may see the whale's approach and react before the whale's sonar locks on. The sequence matters because whoever reacts first controls the opening of the encounter. In some cases, the squid's light detection gives it a warning the whale's sonar cannot provide. The squid sees the glow before the click reaches it. It moves. The whale's sonar locks on a different position. The hunt becomes a chase. And chases in the dark, at depth, consume oxygen. Every second of pursuit is a second off the dive clock. What waits deeper than bioluminescence and squid, the animals that evolved specifically for the very bottom of this world, looks nothing like anything near the surface. Evolution is a simple process with extreme results. In the deep ocean, where food is scarce, light is absent, and the pressure would crush most surface life instantly, animals that survived were the ones built for those specific conditions. Over millions of generations, the deep ocean sorted its inhabitants ruthlessly. The ones that wasted energy died. The ones that waited efficiently lived. The ones with mouths too small to take full advantage of a rare meal left fewer offspring. The result is a collection of animals that look to most people deeply wrong. The fang-toothed fish is a small animal, roughly 6 inches long. Its teeth are proportionally the largest of any fish relative to body size on Earth. The fangs are so long the fish cannot fully close its mouth. They fit into special sheaths on either side of the brain to avoid impaling the animal's own skull when it tries to shut its jaw. The fangtooth hangs in the dark and waits. When something comes within range, the bite is instant and the grip does not release. The barrel eye fish has a completely transparent head. The dome of its skull is a clear membrane filled with fluid, and inside its eyes point upward through the transparent casing, scanning for the silhouettes of prey against the faint light filtering down from far above. The fish is essentially a biological periscope, watching for shadows in the dim zone above it, while remaining nearly invisible from the side. The gulper eel has a body roughly the width of a finger, but a jaw that can open to accommodate prey larger than its own body. The jaw unhinges like a mechanical arm. The stomach stretches to match. The eel drifts, jaw agape, through the dark water and relies on anything swimming into it. The meal, when it comes, can be enormous relative to the predator's resting size. No eyes on many bottom-dwelling species. Sensation replaces vision. Pressure receptors along the body detect vibrations in the water from a distance. Chemical sensors pick up traces of organic material in the current. These animals navigate and hunt without any visual reference at all. The deep is also full of ambush specialists, animals that hold completely still for extended periods, relying on the scarcity of traffic in the deep to make patience a viable strategy. In shallow, busy water, an ambush predator might wait an hour and see nothing pass by. In the deep, that same predator might wait a week, and one meal arrives. Most surface predators cannot operate that way. Their metabolisms demand regular fuel. A great white shark needs to hunt actively to survive. A deep-sea dragonfish can run its metabolism so slowly that a single successful ambush sustains it for an extended period. The sperm whale enters this world as an outsider, a high-metabolism, warm-bodied, air-breathing animal moving through a system built entirely around the opposite principles: slow, cold, efficient, patient. The whale burns through its oxygen reserve at a rate that none of the permanent residents of the deep would recognize as sustainable. It operates on a different timescale, a different energy budget, a different set of rules. It is the fastest, loudest, most energetic thing in a world that rewards stillness. That contrast is part of why the whale is so effective as a predator at those depths. And it is also part of why every second it spends there carries a cost that the animals living permanently around it never have to pay. The deeper you go past the abyssal threshold, the more extreme those contrasts become. And some of what lives at the very bottom is stranger than anything encountered on the way down. The vampire squid is misnamed, and far stranger than its name suggests. It is not a true squid. It is not a true octopus. Scientists classify it in its own separate group because it sits between those two categories in ways that do not fit cleanly into either. Its full name translates roughly to vampire squid from hell, which was given by researchers who first examined a specimen and were, apparently, at a loss for something more measured. It lives between 2,000 and 3,000 feet down, right at the upper boundary of the oxygen minimum zone. A layer of water in the deep ocean, where dissolved oxygen drops to levels too low for most animals to tolerate. The vampire squid lives there, specifically because its predators cannot follow. It has the lowest metabolic rate of any cephalopod ever studied. It can survive at oxygen levels that would kill almost anything else in its size range. Its body is jet black or deep red depending on the light angle. It has 8 arms connected by a webbing of skin, like a cloak pulled around the body when threatened. 2 of its arms are retractable filaments, almost invisible in the dark water, that it extends to collect marine snow drifting down from above. It does not hunt, it filters. The eyes for its size are extraordinary. A vampire squid 4 inches long can have eyes the size of a large dog's. Proportionally, among all animals on Earth, the vampire squid has some of the largest eyes relative to body size ever measured. When threatened, it turns itself inside out. The webbed cloak inverts, wrapping the arms over the body to expose the spiny underside, displaying a shape that nothing in the deep ocean associates with easy prey. At the same time, it can release a cloud of glowing mucus instead of the ink a regular squid fires. The cloud glows blue and confuses a predator by providing a bright, sticky distraction that persists in the dark water, glowing mucus as a defensive weapon. Then there is the siphonophore. A siphonophore is an organism made of individual animals, called zooids, each one specialized for a different function. Some zooids swim, some sting, some digest, some reproduce. They are all genetically identical and physically connected, but they cannot survive separately. The whole colony acts as one animal. The largest siphonophore ever recorded was measured at over 150 feet in length, longer than a blue whale. It drifted in a spiral through deep water, its stinging tentacles extending outward in a grid pattern that anything passing through would contact. A passive trap made of living animals, each one performing a specific job for the larger collective. 150 feet of connected, stinging, hunting colonial organism drifting through the darkness. Below a certain depth, the ocean stops following the design logic of the surface world. The rules change. Body plans become strange, strategies become alien. Animals that would be evolutionary dead ends near the surface thrive in the abyss because the constraints are completely different. And none of it is theoretical. These animals exist right now, in the water beneath ships crossing the ocean. In a world most humans will never directly see, sperm whales pass through this world on their deepest dives. They are surrounded by it on every descent. And they are not the apex predator in every part of it. Near the surface, almost nothing challenges a full-grown sperm whale. But in the water they share with other large predators near the surface, things are different. Very different. Sperm whales are social animals. Females and their young live in groups of roughly 12 individuals on average. They travel together, feed together, and care for each other's calves. When a calf is young and cannot dive deeply, adult females take turns staying near the surface with it, while others hunt below. That social structure has a defensive application that researchers describe as one of the more striking group behaviors in any marine mammal. When danger approaches a group of sperm whales, the animals organize. They do not scatter. They come together in a specific formation called the Marguerite Formation. Named after a flower because of its shape when viewed from above, the whales arrange themselves in a circle. Heads point inward toward the center. Tails face outward. The most vulnerable animals, calves and injured individuals, are positioned in the center of the circle, surrounded on all sides by the large bodies of the adults. The tails facing outward are the weapon. A full-grown sperm whale's tail flukes can span 12 to 14 feet across. The muscle group driving that tail is one of the most powerful in any animal alive. A direct strike from a sperm whale's tail, called a fluke slap, can shatter the hull of a small boat. Against a predator approaching from any direction, the whale closest to it can deliver a strike with force measured in thousands of pounds. The formation means that no matter which direction an attacker approaches from, it faces a tail. Circling to find an angle exposes the attacker to the tails of adjacent whales. Approaching from above exposes it to the group firing sonar clicks upward in coordination. Researchers have documented this formation being triggered by the approach of killer whales, which are among the confirmed surface predators that target sperm whale calves. The formation is remarkably effective. Killer whales are fast, highly coordinated, and experienced hunters and even they struggle to breach a properly formed sperm whale rosette to reach the calf in the center. What this behavior tells us about sperm whales goes beyond defensive tactics. It tells us about memory and recognition. The whales have to know when to form the circle, which individuals to protect, and how to coordinate the formation under stress. That requires communication, situational awareness, and collective decision-making. All of it happening in real time, in open ocean, in response to a threat the group identified and categorized quickly enough to organize a response. The 20-pound brain inside each of those animals is not just for navigation. It holds social relationships, threat recognition, defensive protocols, and decades of learned experience. When people think about what makes sperm whales remarkable, the size comes first, the diving comes second. The brain and the social complexity that brain enables rarely get as much attention as they deserve. But that social structure also has a vulnerability. The times when the group is most exposed are the times when the adults are below and the calves are at the surface, waiting. And the predators that target those calves know exactly when that window opens. Killer whales are the most sophisticated pack hunters in the ocean. They coordinate their hunts with a level of tactical precision that researchers have compared to wolfpack behavior on land: organized, adaptive, and highly effective against prey much larger than themselves. Sperm whales are among the largest animals killer whales target, and the attacks are documented. Researchers in various ocean regions have witnessed and recorded encounters between killer whale groups and sperm whale groups, and the patterns reveal a great deal about how both species operate. Killer whales do not attack adult sperm whales head-on. They target calves. The strategy is to separate or distract the adult group, while smaller, faster individuals work toward the calf. This is why the rosette formation described in the previous chapter is specifically oriented around protecting the center where calves shelter. In documented encounters, killer whale groups typically number between 4 and 12 individuals. They approach fast, coordinating through their own sophisticated communication system. The sperm whale group responds by tightening into the defensive circle. The adults stop diving. They stay at the surface. The calves move inward. What follows is often a prolonged standoff. The killer whales test the formation, probing for a gap, waiting for an adult to move out of position. The sperm whales hold the circle, pivoting collectively to keep their tails toward the approaching animals. The outcome is not predetermined. In some documented cases, the killer whales succeed. A calf is separated, usually when the formation breaks for some reason, and the killer whales isolate and kill it. The adult sperm whales cannot outswim killer whales over distance. Their defense is formation, and once the formation fragments, the advantage shifts. In other documented cases, the sperm whale group holds the formation long enough that the killer whales disengage. The attack fails. The killer whales leave. Researchers have also documented something unexpected in some encounters. Sperm whales from outside the threatened group sometimes arrive during an attack and join the defensive formation. Animals that were not present when the attack began come in from a distance, apparently attracted by the sounds of the encounter, and add their bodies and tails to the circle. That behavior suggests the sperm whales are communicating distress across a wider range than just the immediate group, and that other sperm whales respond to that signal as allies rather than bystanders. Adult male sperm whales are largely solitary outside of mating periods. They roam wide ranges in deeper, colder water. But even some adult males have been recorded approaching and joining defensive formations during attacks, despite having no obvious family relationship with the group under threat. Cooperation between strangers in defense of animals they may never have met. The killer whale, for all its intelligence and coordination, is dealing with a prey animal that may be running a more complex social response than anyone initially expected. And yet killer whales remain a genuine threat to sperm whale populations, specifically to calf survival rates, and therefore to the long-term health of sperm whale groups. The threats above the surface are real and documented, But the behavior of sperm whales under threat tells us something equally important. This is an animal with the intelligence, the social structure, and the learned tactics to respond to danger in organized adaptive ways. An intelligence built partly in the dark during decades of deep dives, sharpened by every encounter that left a scar. A sperm whale calf is born into a social group that immediately becomes its protection system. At birth, a calf is roughly 13 feet long and already one of the largest newborns of any animal on the planet. Despite its size, it is completely dependent. It cannot dive deeply. It cannot outswim a killer whale. For the first years of its life, it needs the adults around it continuously, and those adults need to dive to 2,000 feet to feed themselves. This creates an obvious problem. The animals responsible for the calf's safety are the same animals that must periodically disappear into water too deep for the calf to follow. The group solves this problem through coordinated care. When adult females dive, they do not all go at once. The dives are staggered so that at least one adult remains near the surface at all times. That surface-resident adult functions as a guardian, maintaining proximity to the calf while the others hunt below. Researchers tracking sperm whale groups with acoustic tags confirmed this pattern. The dive timing within a group is not random. Adults coordinate their descent and return to ensure continuous surface coverage. A female returning from a dive often surfaces near the calf before the next adult descends. The calf, meanwhile, learns from the group. Young sperm whales spend years observing the adults, listening to coda patterns, practicing shallow dives, building the physiology and behavioral repertoire they will need as adults. The group is a school in the most direct sense. The knowledge a sperm whale needs to survive is not instinct alone. It is learned from the individuals around it over years of close contact. Mothers nurse their calves for extended periods. Sometimes beyond 2 years, the nursing relationship keeps the calf close to the mother and embedded in the group. Weaning is gradual, and even after nursing ends, the bond between mother and calf remains strong. Females may have one calf roughly every 5 to 7 years. The long interval between calves reflects the enormous investment each one requires. A single calf represents years of nursing, protection, teaching, and coordination. The group organizes itself around that investment. This level of extended parental care is rare in the animal kingdom. It appears consistently in species with large brains, long lifespans, and complex social structures. Elephants do it. Great apes do it. Dolphins do it in a less extended form. Sperm whales do it at a scale that researchers describe as one of the most intensive in any marine mammal. The result of all this care is an individual that, when it matures, carries the accumulated knowledge of its group. Dive locations, hunting strategies, threat responses, coda patterns identifying its family, navigation routes. A sperm whale is not just a large animal with sonar, it is a walking archive of learned information accumulated over decades, passed from one generation to the next, through close social contact in a group that protects its young more deliberately than almost any other ocean predator. What threatens that system is not just physical danger, a disruption to the group structure, a loss of adults, a fragmentation of the social unit, removes the knowledge network that the next generation depends on, and the threats to that structure are real, persistent, and increasingly coming from outside the ocean itself. For all the data researchers have collected, the moment-by-moment reality of a sperm whale hunt at 2,000 feet remains largely invisible. Acoustic tags have given scientists the click patterns. Depth recorders have mapped the dive profiles. Stomach content analysis has confirmed what the whales eat. But the actual sequence of events during an active hunt, how the whale approaches prey, how the prey responds, how the encounter resolves, has never been directly observed in real time at depth. The technology does not yet exist to put a camera on a whale's head, transmit that footage to the surface in real time through 2,000 feet of water, and watch what unfolds. Acoustic tags record sounds and depth, but not vision. Towed camera systems cannot keep pace with a hunting whale. Remote underwater vehicles are too slow and too loud to follow without disturbing the behavior. So the hunt itself remains reconstructed, an inference from the data around it. One of the biggest unknowns is how often sperm whales fail. The stomach contents confirm they succeed regularly. But how many dives result in a missed grab, a squid that evades, a hunt that consumes oxygen without producing a meal? The ratio of successful to unsuccessful dives is genuinely unknown. If a whale fails more often than it succeeds, the oxygen math of each dive changes significantly. Another unknown is how behavior varies between ocean regions. Sperm whales live in every deep ocean on the planet, from tropical waters to the edges of polar ice. The prey available in those different regions varies. Squid species differ. Depth profiles differ. Whether sperm whales in different regions have developed genuinely different hunting strategies, learned behaviors specific to local conditions, is an open question. The evidence that sperm whales have cultural dialects, different coda patterns in different ocean regions, suggests that learned differences do exist across populations. But whether those cultural differences extend to hunting technique is something scientists have not yet been able to confirm. A third unknown is the role of sleep. Sperm whales sleep, and researchers have documented them doing so at the surface in a distinctive posture, floating motionless and nearly vertical in a group, like a set of enormous logs bobbing in synchronized stillness. They sleep deeply enough that boats have passed within a few feet without waking them. But whether they sleep during or between dives, whether there are rest periods built into dive behavior that look like hunting behavior on the acoustic record, is unclear. An animal that spends 45 minutes at a time at 2,000 feet, with a brain the size of a 20-pound organ, needs sleep somehow, and the mechanics of that underwater are still poorly understood. Finally, there is the question of the very deepest dives. The deepest recorded sperm whale dives push past 7,000 feet, well into the range of significant abyssal influence. What the whale encounters at those depths, what it is hunting when it goes that far, and what the abyssal environment at that depth level looks like in biological terms, is largely unknown. The sperm whale goes somewhere humans cannot yet follow. It comes back changed in small ways, scarred, altered, carrying evidence of encounters that happened beyond the reach of observation. The gap in that knowledge is not a small one. It covers the most dramatic part of the whale's entire existence, and closing that gap may reveal that what happens below the sperm whale is stranger than any of the confirmed facts suggest. Sperm whales dive deep, but they are not the deepest divers in the ocean. That record belongs to a group of animals most people have never heard of, beaked whales, a family of medium-sized dolphin-like cetaceans that look, at first glance, like unremarkable ocean animals. Streamlined bodies, small dorsal fins, pointed snouts with a slight beak shape at the front of the face. They are extraordinarily difficult to study. They spend almost no time at the surface. They avoid boats. They are so rarely seen alive in open water that some species have only ever been described from stranded or dead individuals. Several beaked whale species were discovered in the 20th century from bones washed up on beaches, with no living sighting recorded for years afterward. In 2014, a team tagging Cuvier's beaked whales off the California coast recorded a dive that reached nearly 10,000 feet and lasted nearly 3.5 hours. That is the deepest confirmed dive ever recorded for any air-breathing animal, nearly 10,000 feet, 3.5 hours, on a single breath. A sperm whale's deepest confirmed dives reach roughly 7,000 feet and last around 90 minutes at maximum. A beaked whale goes deeper and stays longer. The physiology of beaked whales is not fully understood, partly because they are so hard to study. But what researchers have pieced together suggests adaptations that go even further than those of sperm whales. Oxygen storage capacities relative to body size that exceed expectations. Cardiovascular dive responses more extreme than anything in a sperm whale. What beaked whales are hunting at 10,000 feet is largely unknown. Their diet appears to include deep-sea squid and fish, but the specific species and the dynamics of the hunt are a significant mystery. At that depth, even the acoustic tags used on sperm whales produce data that is difficult to interpret clearly. Beaked whales strand in unusual numbers following the operation of military sonar systems in their areas. The same sonar associated with sperm whale injury events hits beaked whales harder. Mass strandings of beaked whale groups have been recorded following naval exercises in multiple ocean regions, and the pattern is consistent enough that researchers treat the connection as established. The animals that go the deepest are also the most fragile to disruption from sound. A beaked whale disturbed during a deep dive, responding to sonar by ascending rapidly, faces the same decompression risk described earlier, but from a greater depth and with less understood adaptations to manage the ascent. They go deeper than sperm whales. They are seen less. They are more vulnerable to disturbance. And the world they dive into is the least mapped region of the planet. The beaked whale is proof that the sperm whale's relationship with the deep is not the most extreme version of an air breather entering that world. It is simply the one that made it easiest for humans to study. Whatever lives at 10,000 feet and deeper, the things that leave their mark on beaked whales remains almost entirely outside human knowledge, which brings the story to something that does not swim at all, something anchored to the very bottom of the deep ocean that changes everything that touches it. In 1977, a team of scientists lowered a small submarine to the seafloor near the Galapagos Islands, roughly 8,000 feet below the surface. They expected cold, dark, empty sediment. The deep seafloor had always been described as a biological desert. What they found instead changed biology permanently. Cracks in the seafloor where tectonic plates pull apart were releasing superheated water. The water came out at temperatures above 700 degrees Fahrenheit, too hot to be liquid under normal pressure, but kept liquid by the crushing weight of the ocean above. The water was laced with hydrogen sulfide, a compound toxic to most surface life. Around the vents, the rock was stained yellow, orange, and white from the minerals precipitating out of the superheated flow. And living on every surface around those vents was an explosion of life. Tube worms, 6 feet long, clustered in dense mats, anchored to the rock and waving in the thermal current. Pale crabs moving methodically across the vent structures, clams the size of dinner plates, shrimp in massive swarms, a complete functioning ecosystem running entirely without sunlight. On the surface, nearly all life ultimately depends on sunlight. Plants convert it into energy, animals eat plants, predators eat those animals. Sunlight is the base of almost every food web on Earth. At hydrothermal vents, the base is chemistry. Bacteria consume the hydrogen sulfide pouring out of the vents and convert it into energy through a process called chemosynthesis. Other animals eat those bacteria. Larger animals eat those. A full food web built not on sunlight, but on the heat and chemistry of the Earth's interior. This was one of the most important scientific discoveries of the 20th century. It proved that life does not require sunlight to exist. It proved that the conditions most people assume are necessary for life are simply the conditions most life on Earth's surface happens to use. Hydrothermal vents exist across the deep ocean floor in multiple ocean basins. They are not rare geological events. They are a consistent feature of the deep sea floor, and each one supports its own dense biological community. The seafloor that sperm whales occasionally approach on their deepest dives is not the barren wasteland it was assumed to be. It is studded with ecosystems that run on an entirely different energy source, populated by animals that have never seen sunlight and never will. The sperm whale at the bottom of its dive is above a world that has been running independently of the surface for millions of years. And when a sperm whale dies and sinks to that seafloor, what happens next is one of the stranger ecological stories in the entire ocean, because nothing on the seafloor wastes what arrives. The whale that spent its life consuming the deep is about to become the deep's most abundant meal. A sperm whale dies. The body floats for a time as decomposition gases build inside the carcass. Then the gases dissipate, the body loses buoyancy, and it begins to sink. From the surface to the seafloor at 6,000 feet takes roughly 2 hours. During that descent, the carcass is not untouched. Sharks and large fish find it quickly. By the time it reaches the bottom, the exterior is already partially stripped. When the whale hits the seafloor, something remarkable begins. Scientists call it a whale fall, and the ecological sequence it triggers has been studied in detail only since the late 1980s, when researchers discovered a naturally occurring whale fall by chance during a submarine survey. What they found was an entire ecosystem organized around a single dead whale. The first phase lasts months. Large mobile scavengers arrive: sleeper sharks, rat-tail fish, hagfish, and others. They strip the remaining soft tissue from the bones. The carcass can lose over 90% of its soft tissue mass in this phase. The feeding is intensive and involves hundreds of individual animals working simultaneously. The second phase begins as the large scavengers thin out. Smaller animals colonize the skeleton. Polychaete worms, crustaceans, and snails move into the remaining tissue trapped in joints and cavities. These enrichment opportunists work more slowly, extracting nutrition that the large scavengers bypassed. The third phase is the strangest. Sulfophilic bacteria colonize the lipid-rich bones. Whale bones are full of fat, and as that fat decomposes anaerobically, it produces hydrogen sulfide, the same compound that powers hydrothermal vent communities. The same chemosynthetic bacteria appear. Similar worms and crustaceans colonize the surface. A dead whale becomes a temporary hydrothermal vent on the seafloor. This sulfophilic phase can last decades. The bones of a large sperm whale contain enough lipid to sustain the chemical reaction for 50 to 100 years. For a century, a single whale's skeleton supports a dense biological community on the otherwise sparse seafloor. Researchers studying whale fall communities have found dozens of species that appear to live almost exclusively on whale falls. Animals specialize to the specific conditions that a decomposing whale skeleton creates. Some of those species appear at multiple whale falls across different ocean basins, suggesting they disperse through the deep ocean between whale falls, moving from carcass to carcass across vast distances. One dead whale sustaining a unique ecosystem for 100 years. Scale that across the historical sperm whale population. Before commercial whaling reduced their numbers severely in the 18th through 20th centuries, tens of thousands of sperm whales died natural deaths each year and sank to the sea floor. The deep ocean floor was dotted with active whale falls in various stages, creating a distributed network of chemosynthetic islands across the abyss. Commercial whaling removed a significant portion of that input. Fewer whales dying naturally means fewer whale falls, which means fewer of the species dependent on them. The loss of sperm whales from whaling did not just remove whales from the ocean, it changed the ecology of the deep sea floor in ways that are still being understood. What remains at the bottom, beyond the whale falls, are sounds. Sounds recorded by researchers that have no confirmed source. Sounds that the seafloor produces and that nothing in the known catalogue of deep ocean animals fully accounts for. The number 100 years sits with most people for a moment before it fully lands. 100 years of sustained ecosystem productivity on the otherwise sparse abyssal floor. To understand why that number is real, you need to understand the lipid content of whale bones. Bone in most animals is primarily calcium and protein. It is dense, relatively dry, and offers little nutritional value once the marrow is extracted. But in deep-diving marine mammals, bone structure changes under evolutionary pressure. The bones of a sperm whale, particularly the large vertebrae in the skull, are permeated with fats and oils in a way that the bones of most land animals simply are not. Those lipids are the fuel source for the sulfophilic phase of a whale fall. The anaerobic bacteria that colonize the bone after the surface tissue is gone break down those lipids through chemical processes that produce hydrogen sulfide as a byproduct. The hydrogen sulfide then feeds the chemosynthetic bacteria, which feed larger animals, which feed larger predators still. The deeper the whale falls, the longer the process tends to last. Colder water slows biological activity. Lower temperatures reduce the rate at which bacteria metabolize the bone lipids. A whale falling to 6,000 feet will decompose more slowly than one falling to 2,000 feet, simply because the cold is more intense and more consistent at greater depth. A large sperm whale on the deep abyssal plain can sustain active sulfophilic communities for close to 100 years under the right conditions. That figure comes from researchers who have sampled whale falls in various stages of decomposition and modeled the lipid depletion rates. The community living on an old whale fall is genuinely dense by abyssal standards. Bone surfaces are carpeted with tube worms, covered in mats of bacteria visible to the naked eye, crawling with specialized crustaceans and snails. The immediate area around the skeleton shows higher concentrations of life than the surrounding seafloor, sometimes dramatically so. This density creates its own predator community. Animals that would not otherwise have reason to congregate in one spot are drawn by the productivity of the whale fall. That brings predators who feed on those animals. The whale fall functions as an oasis, concentrating life in a way that the flat, nutrient-poor abyssal plain rarely produces on its own. Researchers have estimated that a single large whale fall can support more individual organisms over its active lifespan than most patches of equivalent seafloor area would see across the same period. One death generates more total life than the surrounding environment does across the same time frame. There is something genuinely striking about that. The whale spends its entire life consuming enormous quantities of squid and fish from the deep ocean. And when it dies, it pays that back in full, releasing its stored energy into the ecosystem over a century of sustained productivity. The sperm whale is not just a predator in the deep ocean. It is a contributor to it in ways that only become visible long after the animal is gone, which makes what humans did to sperm whale populations during the height of commercial whaling a different kind of loss than the obvious one. The animals removed from the ocean took their whale falls with them. The ecosystems those falls would have sustained for decades never materialized. The bones that never reached the seafloor represent communities that never formed. Species that may have declined without the distributed network of chemosynthetic islands that a healthy sperm whale population would have maintained. The consequences of that loss are still playing out in the deep ocean below us. In 1997, researchers operating an underwater sound monitoring network in the Pacific Ocean detected something unusual, a sound so loud it triggered sensors across a span of roughly 3,000 miles of ocean. The sensors were designed to detect broad acoustic events, and this one covered an area larger than the continental United States. Scientists named it the bloop. The sound was unlike anything in the confirmed catalogue of ocean acoustics. It rose sharply in frequency over about 1 minute, with a profile resembling biological sounds rather than geological ones. It was too loud to be any known animal. It was too biologically shaped to be a simple geological event, like an earthquake or a volcanic eruption. For years it remained unexplained and attracted widespread speculation about unknown deep ocean creatures capable of producing sounds at that scale. In 2012, scientists revisited the recording with updated analysis tools and concluded the most likely source was an icequake, a large fracture event in Antarctic ice, which can produce sounds with biological-seeming profiles when filtered through long distances of ocean. The explanation satisfied many researchers. Others noted that the icequake explanation matched the frequency profile but left some features of the recording unaccounted for. The bloop is the most famous case, but the Deep Ocean Sound Catalogue contains other unexplained recordings. The upsweep has been recorded periodically since the early 1990s. It consists of a sustained series of narrowband upsweeping sounds, appearing seasonally and originating from somewhere in the South Pacific. No confirmed source has been identified. The slowdown is a sound recorded in 1997, similar to the bloop in geographic scale, but with a different frequency pattern. Scientists believe it originated near the equator in the Pacific and traveled across most of that ocean's width before being detected. The train is a low-frequency sound recorded in the early 1990s with a very regular, almost mechanical rhythm. The origin is unknown. None of these sounds are proven to come from biological sources. Geological explanations exist for most of them and are generally accepted by the research community. But the honest position is that the deep ocean is still generating sounds that require ongoing analysis to fully characterize. And that is in a monitoring network built specifically to detect nuclear test detonations, a system sensitive enough to pick up events across thousands of miles of ocean. What occurs at scales below that detection threshold, sounds that are large biologically but too small for the global network to reliably capture, is essentially unmonitored in most of the ocean. Sperm whales hear the ocean at frequencies and sensitivities humans cannot match. They live in an acoustic environment we have only begun to map. What those whales are reacting to in their behavior, what sounds they detect that our instruments miss, is a question with no current answer. The ocean is full of sound. Most of it we understand. Some of it we do not. And the portions we do not understand tend to come from the same depths where the sperm whale hunts, and the same regions where the strangest animals on the planet make their lives. What those sounds represent is still an open question. What they mean to the animals that actually hear them is something we may be decades from understanding. A sperm whale on a beach is a disturbing sight, an animal built for the deep ocean, perfectly adapted to pressure and darkness, lying in inches of water under open sky. The scale of it surprises people who have not stood next to one. The head alone, that massive rectangular structure, is as long as a pickup truck. Strandings happen. They have been documented throughout human history, and they occur in patterns that researchers have spent decades trying to understand. Some strandings involve single animals. A lone whale beaches itself, often showing signs of illness, injury, or disorientation. These individual cases frequently involve animals that are already in serious physiological distress, weakened by disease, gut impaction from swallowing plastic debris, or injuries from ship strikes. The beach in many of these cases is the last stop in a longer failure event, rather than the cause of the animal's death. Group strandings are different and more puzzling. Multiple sperm whales beaching simultaneously, sometimes dozens at a time, has been recorded in specific geographic locations around the world, particularly in certain stretches of coastline in the United Kingdom, New Zealand, and parts of the eastern United States. One proposed explanation involves the deep-water mapping abilities of sperm whales. The animals navigate partly by reading the geography of the seafloor through their echolocation. In certain coastal areas, the seafloor topography creates what some researchers describe as acoustic dead zones, regions where the returning echoes from the sonar give a misleading picture of the geography ahead. Shallow, gently sloping sand beaches produce poor sonar returns in some conditions, appearing in the echo as open water rather than a closing shoreline. A whale navigating by sonar in most conditions may not detect the beach until it is already in water too shallow to turn around effectively. Another factor is group cohesion. If one animal in a tight social group makes a navigational error and moves toward shore, others in the group follow. The same social bonds that make the defensive rosette effective, the deep loyalty to the group, and the tendency to follow group movement, can become a liability when one animal goes wrong. Military sonar events have been associated with group strandings in some documented cases. Sudden, intense sound exposure appears to cause rapid ascent behavior in deep-diving whales, and the disorientation following a severe sonar event may disrupt navigation enough to produce coastal stranding. Post-mortem examinations of stranded sperm whales have found a range of contents in their stomachs that reflect the state of the ocean they were living in. Squid beaks, fish bones, and, increasingly, plastic, bags, nets, fishing line, rigid containers, animals that died with dozens of pounds of plastic blocking their digestive systems, gut impaction severe enough to prevent feeding, and ultimately cause starvation. A sperm whale starving to death from a blocked gut is not dying from what lives below it, it is dying from what humans have put in the ocean above it. The beach where it strands is the last place a deep ocean animal should ever be. And it is there because something above the surface, and increasingly the state of the surface ocean itself, pushed it out of the world it was built for. A sperm whale's survival depends entirely on sound. Its hunting depends on sound. Its navigation depends on sound. Its social relationships are maintained through sound. Its ability to find mates, coordinate with its group, and detect threats all run through an acoustic system that evolution tuned over millions of years to function in a specific sonic environment. That environment no longer exists in most of the ocean. Commercial shipping routes cover nearly every major ocean basin. A large container ship generates continuous low-frequency noise that travels thousands of miles through deep water. The ocean that sperm whales evolved in was acoustically quiet over long distances, punctuated by biological sounds and occasional geological events. The ocean those whales live in today has a constant global layer of human-generated noise blanketing the frequency ranges most relevant to their communication and echolocation systems. A sperm whale trying to navigate a busy shipping lane is doing so in conditions analogous to trying to have a quiet conversation while standing next to a highway. The signal is present. The noise is louder. Researchers tracking sperm whale groups in heavily trafficked ocean regions have documented behavioral changes consistent with acoustic masking. Whales calling more frequently to maintain contact with group members, as if compensating for signals lost in the background noise. Whales surfacing in unexpected locations relative to their expected dive trajectories, suggesting navigational disruption. Some research has found that sperm whale click rates change near shipping traffic. The whales are adjusting their sonar behavior in response to the noise environment. Whether those adjustments fully compensate for the masking or whether hunts are less efficient as a result is still being studied. Military sonar operates at frequencies and intensities well beyond commercial shipping. Active sonar systems used in naval exercises emit extremely loud, directed sound pulses that can travel hundreds of miles through deep water. The association between military sonar and cetacean strandings is one of the more clearly documented relationships in ocean noise research. Sperm whales are somewhat less sensitive to mid-frequency sonar than beaked whales based on available evidence, but several documented mass stranding events have included sperm whales in areas where naval exercises occurred in the preceding days. Oil exploration adds another layer. Seismic surveys used to map geology beneath the seafloor fire airguns at regular intervals, producing short, extremely loud pulses of sound designed to penetrate the seafloor and reflect back. Those pulses occur repeatedly, sometimes every 10 to 15 seconds, for days or weeks during a survey. In active survey zones, the sound environment in the ocean changes dramatically. Sperm whales in regions with active seismic surveying show reduced foraging behavior and altered movement patterns in some studies. The hunts become less frequent. The dives change. The whale is being pushed away from its hunting grounds by sound it cannot avoid. The animal that evolved the most powerful biological sound system on Earth is now operating in an ocean louder than anything its biology was built for. What it can hear of its own world is being progressively crowded out by the sound of ours. And the parts of the deep that remain genuinely quiet, the parts that sperm whales may favor precisely because of that quiet, are shrinking. Less than 20% of the ocean floor has been mapped with meaningful resolution. The surface of Mars has been mapped more completely than the bottom of Earth's ocean. That comparison is not rhetorical. It is a measurement of actual survey coverage, and it says something important about the limits of what humans know about the planet they live on. The deep ocean covers more of Earth's surface than all the land on every continent combined. Most of it has never been directly observed. The portions that have been visited by submarines or cameras represent a tiny, non-random sample of the total. Researchers target areas of particular geological or biological interest, which means the unremarkable-looking stretches of the abyssal plain, which make up the vast majority of the deep-sea floor, have almost never been visited. New species are discovered in the deep ocean every year. In many survey expeditions to unmapped areas, a significant portion of the animals collected or photographed are species new to science. In some expeditions targeting specific deep-sea habitats, the majority of animals observed have been previously unknown. Several large animals have been discovered in the last century that people did not know existed. The megamouth shark, a filter-feeding shark reaching roughly 18 feet in length, was first described in 1976, after one was accidentally caught by a naval research vessel. Before that discovery, no one knew an animal of that size and type existed. It had been swimming in the ocean for presumably millions of years while humans lived on the surface above it, with no idea. The colossal squid was not confirmed as a species until the early 20th century. For years before its formal description, fragmentary evidence, sucker marks on whale skin, partial specimens in whale stomachs, suggested something very large lived in the deep Southern Ocean. The full picture of what that animal was took decades and multiple specimen collections to assemble. What remains unknown in the unmapped areas of the deep is genuinely impossible to estimate. The tools available to researchers, submersibles, towed cameras, acoustic surveys, sampling nets, each capture only a narrow slice of what is present in the water or on the sediment at any moment. Animals that are rare, fast, transparent, or simply located between sampling stations go undetected entirely. Researchers working in the deep routinely describe encounters with large, fast-moving objects that pass through camera frames too quickly to identify, or sonar contacts that are too large and mobile to be explained by any known species in that depth range. Those contacts are not proof of anything beyond the known catalogue. They may be known species in unusual postures, or known species whose behavior at depth differs from what has been studied at the surface, but they represent the honest limit of current knowledge. Sperm whales have been hunting in those unmapped areas for millions of years. Their scars are evidence of animals that may not yet be formally catalogued. Their stomach contents, in some cases, contain beak fragments that do not match any described squid species. The whale knows what lives there. We do not. That gap between what the whale encounters and what humans have documented is one of the most significant known unknowns in all of biology. The ocean is not fully mapped. The deep is not fully explored. And the evidence that something significant still waits to be found, carried on the skin of the largest toothed predator alive, is as clear and as literal as a circular scar the size of a dinner plate. Pull back from the individual dives, and the squid encounters, and the bioluminescence, and the pressure calculations, and look at the full picture. A species of animal has been living on this planet for millions of years. It grows to 52 feet and 45 tons. It has a brain weighing 20 pounds, organized around acoustic processing and social memory at a level of complexity researchers are still mapping. It dives to depths that kill most other air-breathing animals. It hunts prey that no human has ever directly watched it catch. It carries a cultural tradition of learned dialects passed from mother to calf across generations. And it maintains social structures sophisticated enough to coordinate collective defense, cooperative childcare, and long-distance communication. This animal has been doing all of this continuously in the deep ocean for longer than our species has existed, and we learned most of what we know about it in the last 50 years. That timeline matters. 50 years ago, scientists did not know sperm whales had dialects. They did not know about the rosette formation in detail, They did not know the mechanics of the lung collapse at depth. They had not confirmed giant squid on film. They had not documented whale fall ecosystems. They did not have acoustic tags, depth recorders, or the analytical tools to reconstruct dive behavior. Everything we now understand about the sperm whale arrived in a few decades of accelerating research, and the researchers doing that work consistently note that every answer produces more questions. The scars remain partially explained. The deepest dives remain unobserved at the moment of the hunt. The exact identity of the largest prey remains uncertain in some cases. The content of beaked whale stomachs, which suggests they access depths even the sperm whale rarely reaches, remains largely unknown. The beak fragments in whale stomachs that do not match described squid species remain unresolved. The ocean covering most of this planet has been operating as a complex, layered, biologically rich system for hundreds of millions of years. The animals in it have been competing, adapting, and shaping each other across timescales that dwarf recorded human history. The sperm whale is one data point in that system, an exceptional one, but still one node in a network of interactions we have barely begun to trace. What the sperm whale's existence tells us is that the most extreme behaviors, the deepest dives, the largest prey, the most sophisticated social structures, happen in places we cannot easily observe. They happen in the dark. They leave only indirect evidence, and the evidence we do find, the scars, the beaks, the acoustic recordings, the dive profiles, consistently points toward a reality more complex and more extreme than the previous model assumed. Every time researchers have extended their tools into deeper water, they have found more than expected. More species, more interactions, more organized behavior, more ecological significance to processes that seemed marginal from the surface. The sperm whale dives into a world that runs on different rules than the one we live on. It has been doing this since before humans existed. It will continue doing it if it survives what the surface world is doing to its ocean. For as long as the deep water exists, what lives below it is still being discovered. What those discoveries will mean for our understanding of life on this planet is a question that only the next generation of deep ocean research will answer. The whale goes down, the darkness closes over it, and somewhere below, in a place humans have never seen and may not see for decades, something very large is waiting.